Really interesting panel discussion led by Chad Hart. Chad Hart is a thought leader in WebRTC, blogs at WebRTC Hacks and Cogent.ai, where he explores the use of artificial intelligence and real-time communications. Also an organizer of the Cranky Geek conference series, which is excellent as well. For those of you interested in WebRTC, you probably already know it. And in addition is a consultant and product manager to a number of, has worked with a number of companies in the WebRTC space, including CallStats. And very pleased to have Chad here today leading this panel on RTC in a world of AI and ML. So Chad, right. Thank you.
Yeah, thanks so much, Aaron. So since Aaron, actually, I appreciate the great introduction. I'll skip over this. I'm also going to ask I'll have the panelists introduce themselves during their sessions. But first I wanted to talk through and just establish a framework. So last year I actually did a market research study on looking at the use of artificial intelligence and machine learning within real-time communications. And I published a report with Sadia Levant-Levy, who's another analyst. And in our research, we found 4 main categories of AI and RTC use case, and I'll walk through each one of these. The first is speech analytics, and actually this one's been around for the longest. Things like transcription obviously come into play here, but even going beyond converting speech to text, there's a lot involved in doing natural language understanding, interpreting, and encouraging action. And traditionally, speech analytics, and this is actually a screenshot from one vendor in this space, CallMiner. A lot of it was really set up around call centers. Call centers, generally are big cost centers or revenue centers. There's a lot of money there, and speech analytics was traditionally pretty expensive, but it could be justified if you can improve the agent performance or customer satisfaction, even by just a few percentage points. You can justify spending hundreds of thousands, millions of dollars. But the challenge here is that this technology traditionally was limited to very large call centers, people just willing to pay a lot of money. And this is really starting to change quite a bit over the last several years. First, with a lot of the very cheap cloud APIs from people like Google and Amazon out there, and with some other smaller specialists now popping up. And in addition, now the open source products here are really maturing quite a bit. With a number of really great initiatives. So this is really changing the dynamics of the industry and opening it up to a lot more use cases. Another one is probably my favorite is Voicebots, right? And we all have like Google Assistant or Alexa or Siri at home, and this technology's that technology for consumer purposes has been evolving very rapidly. And traditionally, a lot of that technology, again, was limited to very high-end, expensive type call center type scenarios. And this is really starting to change, right? And a lot of these little technologies as part of the stack, I won't go through all the details, but there's really great open source products. And in addition, there's billions of transactions happening with these consumer-oriented smart assistants. And those companies are like Google and Amazon are turning their attention towards towards voice and telephony use cases in the IVR market. So I think this will be really exciting to see, as that technology, which really the consumer-oriented stuff just serves so many more people and has evolved so much more rapidly, is going to quickly overtake some of the incumbent conversational IVR technologies. Another common one is computer vision. So many of you have probably seen just the Funny Hat app when you make a call with your favorite video calling app out there. But this goes beyond just Funny Hats. Just the ability, particularly in business type use cases, to identify faces, identify people, count people, and going beyond that, improving communication by helping with emotional analysis. And a lot like the speech analytics, this is becoming really, really easy to do with frameworks like TensorFlow. Here's an example I did on WebRTC Hacks a couple years ago that really didn't take too long at all, just hooking up a WebRTC real-time communication stream up into TensorFlow to do real-time object detection. Right? And this was just done on my laptop without any special hardware. But some of the more exciting things that are happening now is that a lot of this is pretty processing intensive type activities to run these neural networks. This technology is being shrunk down and put on specialized chips. And here's an example of like AIY Vision Kit, which is another project out of Google, where actually you can run a neural network right on the chip. And you're starting to see this a lot more, even with a lot of these frameworks being built into iOS and not into Android. So now, being able to do this computer vision processing is not always an expensive server-side task. It's something you can do relatively cheaply by leveraging edge devices. And the last area I'll touch on is RTC optimization, just generally making use of machine learning to help improve real-time communication, connection quality, and routing. I don't know why it's coming in out. And one of my favorite examples here is Mozilla has an open source project, RNNoise, and they're using machine learning to help with noise suppression, right, using deep learning. And this is just one great example, and the panelists will talk about more of where real-time communications machine learning can be used to help a lot of the traditional VoIP stack of what we do. So our format for today, we'll spend about 15, 20 minutes, and I'll ask each of the panelists to come up and just give an introduction to how their individual companies and how they're making use of machine learning and how that fits in real-time communications. And then we'll just have an open roundtable discussion. I have a number of topics here, but you'll have a chance in the audience to ask questions along the way here as well. So with that, I'll invite up Chris Wendt of Comcast. And Chris, I'll ask you to just give yourself an introduction. Load up your slides. There you go. Thanks.
Thanks, Chad. Yeah, I'm Chris Wendt. I'm Director of Technical R&D for IP Communications at Comcast. I've given talks in the past at this conference on both my RTC hat as well as some people might know me in my Shake and Stir hat as well. But today I'll focus on RTC. At Comcast, I lead a software team that builds a real-time communications platform that extends our traditional telephony products, both on residential side and on the commercial side. So we're building a lot of over-the-top type of applications, things that support your traditional, conferencing and other solutions for commercial and business purposes. And we offer those to customers. So today I wanted to talk about, from like a service provider perspective, how we're using machine learning. And, there is a lot of cool things, like Chad talked about RTC. I'm going to talk a little bit about that. But we also use machine learning for a lot of other things that maybe, if you're not familiar with the space, you might not expect. So, there's the application level, like I said. There's one big thing that we use it for is operational purposes, so fault detection, anomaly detection in the network, making sure our services are reliable, making sure they're up and running, making sure they're healthy, detecting things that we might not be alarming on that are happening in the network. I'll talk about that framework. And then the third part is just general data analytics. So, in the telephony space, there's a lot of fraud and spam going on, as you all probably know. So looking at that and trying to detect when those things are happening, people are, stealing services or, like making calls that they shouldn't be, or stealing account credentials and placing fraudulent international calls, things like that. And then there's also the quality of experience
collection of data and making sure that people are having a good experience. So I tried to put together like a couple of pictures on the general frameworks that we're building into our platform. They're pretty generic, so like if you're familiar with this space, it probably looks pretty standard. But you know, I think, you know, it's turned out like these things actually sort of work the way as advertised. So as you may or may not know, a lot of the machine learning techniques that people are using are based on neural networks. And when you build a neural network model, a lot of data has to typically go into that. So you collect a lot of the indicator data that is associated with whatever pattern you're trying to match. So, you know, if it's object detection in video, you need let's say facial detection. You need to put a lot of faces into the data and build a model on top of that. If it's audio, like speaker detection, you want to detect somebody's voice, you need to put a lot of data in and build a model around that. And it's typically a pretty expensive process. So this is just demonstrating the, you know, pre-processing. You typically need data that you also know, like the answer to that data, like this is a face, this is a human face versus a cat or a dog or something like that. You push that all through, you calculate your neural network model. You do a lot of fine tuning as well, so there's sort of an art to that approach, and then you generate the model that is used in the next parts of the process. So first, on the application side, for us, application is usually video, audio, chat. So either, you know, computer vision or audio processing, or for text, it's usually natural language processing. Typically we have like this front end thing, so you build a model, you have something that can run on the client in a reasonable amount of whatever CPU power that the model has. So so, you know, like if it's the like Alexa model where it's trying to detect a keyword, you have something a model that's built that'll detect that somebody utters a keyword. If you're looking for a specific video object, you're looking like maybe generally like, oh, I think this might be, you know, a human outside my front door versus, you know, a car passing by or whatever. Or in text, you know, you might be looking for a particular phrase or sentence or particular subject matter. You look for those things generally. You create an event that registers that said, oh, I think this might be happening. And then you pass it back to the back end where you typically have more processing power, bigger models, more comprehensive techniques of doing machine learning. And then you either qualify that that event actually happened, or extract additional metadata about that event, or things like that, and then you can, you know, associate that metadata with whatever event. So we use event as sort of a generic thing. It could be, you know, a video event, an audio event, chat event, things like that. That's application layer. On the operational side, you know, we have a lot of systems that are generating application logs. They're generating KPIs, metrics, monitoring is going on, sending out streams of data. We typically store these in some time series database, and then have some process that's going on that is looking for features within those things. You know, a lot of times in logs, sometimes the applications generate errors and alarms directly, so you don't necessarily have to do any machine learning techniques to do that. But then there's underlying things where, you know, it's the things that you haven't, as a developer, haven't predicted that you want to look for. So like underlying, you know, things where maybe the, you know, like if there's a memory leak and it starts building up and it's not like there isn't a particular point that, you know, it's been detected, but underlying the trends of the data that's coming out of the machines is sort of like starting to grow and build up, and that's something you might alarm on. And then just general metrics, so like, you know, looking at the overall historical utilization, or you know, how engaged your users are, or other things like that. What's that? Okay, I'll quickly go through this last one. And then the last one, which is, you know, pretty straightforward, is, you know, this is more specific to traditional telephony, where we have CDRs that we collect, and then we collect that data into some time series database, and then we do like MapReduce style analytics, and you know, algorithms to detect either fraud or other quality of experience types of metrics out of the call data. So that hopefully gives like an overview of you know, like the general uses of machine learning in real-time communications related systems.
Great, thanks, Chris.
Thank you.
As I said, each of the panelists will just do a short talk, and then there'll be plenty of time for questions. Varun.
Do you have my slides?
I do.
Hi, I'm Varun Singh, CEO and founder of CallStats.io. Oh, it's part of going forward. So we started building CallStats about 5-6 years ago, and the whole idea was, okay, it's in some, was to measure quality of experience by, similar to how you do web page performance monitoring. So you put a JavaScript or you add a library to your application, which gets loaded on each end user side when they load the web page. Similar to that, we took that same model and said, okay, we want to collect data at very large scale as WebRTC gets adopted. And the main reason for that was, as WebRTC was being adopted, these products needed a new way of monitoring, especially as audio and video got encrypted, like getting data from the middle became increasingly difficult. So if the payloads are, if the whole RTP is encrypted, then you would not see any of the data unless you were at the endpoints. So the mission and vision of CallStats became like, how can we help these people who are deploying WebRTC products at scale? How could data help them build a more compelling product? And with CallStats, the idea became that we would start collecting data, and initially was to visualize the data and help people figure out what's going wrong with a particular call. So a lot of it was just collecting the data, visualizing it. And as we progressed into year 3, we realized that we were sitting on a lot of data where we could actually start to make sense of this data, or help customers or help people across organizations make better decisions, right? So especially as a SaaS product, we were monitoring product A and monitoring product B. Especially with product C that was coming on to using WebRTC, even if you had 0 data, you could actually leverage CallStats to like jump through some of the teething problems that we've already experienced with other that we've seen with other products. So basically, you come and integrate CallStats, and you start as if you had a lot of data from day one. So where are we using machine learning or AI? So there are 2 aspects of it. One is within a call, and the other is outside of a call. So within a call, it means like doing time series analysis to figure out what are the anomalies, if there's packet loss, if there's high latency, if there's jitter, if there is any of the network statistics, does it affect like the audio and the speech? So like looking at the data from the front of the pipeline to the end of the pipeline, and seeing like if there's a causal or a correlation between like rendering issues, and like network issues. Right, so that means like you can figure out annoyance detection, you can correlate user feedback at the end of the call if someone gives a low rating to a call, being able to like see if it actually, if there was perceptible reason for a low user feedback, you would want to like go and compare that or correlate that with actual data in the call. And overall, what you want to do with the data is to be able to predict quality of experience, right? So like now that you have like from the data from the whole call, you have user feedback, you want to be able to say like, oh, these things or these artifacts or these annoyances have actually perceptible value or meaning, and hence this should affect the call in a certain way. And once you have all this data, you want to be able to correlate this across your calls or benchmark against other services, which would mean like if you're a globally deployed system, you want to know like if your calls that are happening in a certain geography or a certain application version, like how does that contrast and compare with each other. So taking the bigger problem first, so if you're doing AI or ML for what we call assisted decision making. So if you have a lot of data and you have like operational teams where they're looking at alerts, and especially operational teams if could are really good at figuring out urgent issues. So as soon as something happens, they go and like learn from that experience and put thresholds around it. So like for example, if like quality of experience declines dramatically in a particular region, once that happens the first time, the second time around, you basically go and set an alert for that, right? And so more mature operational teams actually already know of that and actually avoid a lot of these issues by like setting up traps and alerts. But the question becomes like with large-scale deployments is like, have you set up alerts for everything, right? So like maybe your application is growing in a new geography that you had not thought about to put an alert on. So basically what we realized is that since we are monitoring all the data in real time, we could like look at all the data and the trends and train our systems to actually go and look for these hidden emergent issues, and especially think of like if your product's being used differently in a certain part of the world, it would basically understand that this is a new trend, and if that trend is increasing or declining over time, it would then start to send alerts for it. So the main advantage here is that your operational team is not looking at trying to figure out what those alerts are. The system's already alerting them, and what they're doing is like trying to figure out if these alerts are of significance to them, right? So like take away the responsibility or the mundane activity of trying to figure out if how to avoid outages, but rather looking at things that would predict outages and then you catch them early. So that's the machine learning for decision making, right? And the second thing, so how it shows up is typically like as an alert, and you can think of this like swipe left, swipe right. Like if an alert shows up and you think that's interesting, you swipe right, and if it's not interesting, you swipe left. If it's urgent, you escalate by a swipe up, right? So it's very similar to other products in the market which do the same thing. And application optimization, this is what the in-call API was for. So basically when you start a call, the question always comes up like, what is a good start bit rate? What is the start resolution? Should I be doing 4K? Should I be using my Wi-Fi or 3G? And should I be starting at high bit rates or low bit rates, right? And these are a lot of this is the responsibility of the application developer. So if you're a Snapchat, you may actually do differently from like a Hangouts, from a FaceTime. And a lot of people focus on this starting quality of experience. And the problem becomes very complex as soon as you notice that your app is being actually used globally. So how do you like set up a setting for something in Singapore versus something in Tokyo or something in the Middle East, right? So, and there might be different issues. There may be firewalls. There may be like bad ISPs, ISPs that do rate control, and so on and so forth. So the whole idea here is that that if there's a system that's monitoring each and every session, it would figure out based on your context and app constraints what is the best thing to do. So it can use prior knowledge based on previous calls, or it could actually be based on a recent call or people in the same geography. So even though I've not made a call from, let's say, this location, but there are several students here who made calls in the past, and if we can leverage that information to make these decisions, that would be helpful. Like especially if I'm using an iPhone, I'm using the same app as a previously used app, let's say Slack, then if I'm going to make a Slack call right now and someone's already made this call like 5 minutes before or 2 days before, I can use that knowledge or that historical evidence of an iPhone here making a Slack call and apply it. So I think this is the overall context of how we use machine learning. I'll leave the rest of my time for the rest of the speakers.
Great, thanks. Yeah, VJ to come up.
So thank you very much. I'll try to keep this brief. My name is Vijay Gurbani, and I'm wearing at least 2 hats today. One is in my capacity as the Chief Data Scientist for Veil Systems, which is a company I joined last year. And there I'm responsible for putting together vision and moving AI products ahead in our various portfolio of the companies that we have. And my second hat is that of a adjunct professor here at the Illinois Institute of Technology, where I teach machine learning and data mining. So with those two, I'm going to briefly give you an idea about Veil, and then I will give you a couple of reasons why we want to do AI. I'm not going to go through all of the excellent reasons that my colleagues mentioned, and I'll focus on just a couple of them and then turn it over for further questions. So Veil was founded in 1991, and since then the company has grown pretty much year over year. It grew 45% 2017 and 2018. And if you are a graduate and if you have a good publication portfolio and good research work in machine learning, especially applied to real-time communications, by all means, drop me a line. Our core platform represents over 50 million in cumulative R&D, and we work with one of our biggest customer, Level 3 CenturyLink, essentially to OEM some of our products. So wherever CenturyLink provides access to customers, we can have our products be available to those customers. So to give you a brief idea, we handle about 7 to 10% of call center traffic in the United States. So essentially, we get access to the RTP media stream as well as the SIP signaling part, and we can create all kinds of interesting models that run across the company. So one of the things that really we have been doing for a long time is understanding the value of speech. And this is important, right? You can see it today with all these chatbots, and you can see it with Siri, and you can see it with Alexa. Speech is indeed the central tendency, right? It's a central component of how we as humans, form societal bonds and cultural bonds, right? So if you take a look at transcription, yes, we use deep neural networks to produce that transcript, but what is the value of that transcript, right? We are going to use that transcript to do something. It might be fraud detection, it might be some other type of thing, but the transcript in and of itself is not the end result. The end result is going to be something else, but we want a transcript that's fairly solid, right? There is a lot of work that goes on in NLG to produce a transcript, and no matter how deep your learning model is, if it's not trained on a particular area, it's going to have problems mistranscribing certain words. Or consider, for instance, the words consider it and considerate, right? Consider it. I'm a considerate person, and I'll consider it. Or consider, for instance, efficient and deficient. Those are antonyms. Where does a transcription system know that it should put efficient and deficient if it didn't hear quite what was said because of noise on the channel, for instance, right? So what we want from these transcripts is essentially to take all this noise out and form a narrative from the transcript, and then use that narrative and apply it to certain models. In computer science, there's a whole lot of work going on in something called affective computing right now. Affective computing essentially is having systems simulate human effects. So imagine that you call a call center, and imagine that they have a voice bot that's greeting everybody that calls, and imagine that you're having a great day and you're very, very positive on everything, and you go, hey, and the call bot goes, hello, how may I help you? Right? That's not going to go very far. If the caller is in a good mood, we want the voice bot to automatically mimic that mood, right? So if the caller goes, hey, do you have a second? We want the voice chat bot to go colloquially, of course I do. How can I help you? Right? And so on. We do not want restricted grammars. Certain grammars have to be obviously restricted because we don't have computers that pass the Turing test today. But we do want to have fairly flexible grammars, and we do want to have this notion of effective computing going through our various machine learning models. So with that said, I think I'll turn it back to Chad, and and then, you know.
Great.
Please.
Yeah, thanks, Vijay. All right, so now we're going to switch and have some roundtable discussion, and I'll actually let you in the audience ask some questions in just a moment. But I have a bunch of my own. So maybe to start, I'll combine the first two questions a little bit. Can each of you talk a little bit about how you're implementing your machine learning and how you're doing it? What frameworks, what methodology are you using? Are you using open source tools? Are you using commercial APIs or cloud APIs? Maybe Chris, we'll start with you.
Sure. I'm going to use my cheat sheet here, but most of our development, we use a lot of open source tools as part of our stuff. Our main framework is Keras, and I think it both has hooks into like TensorFlow and PyTorch. Like those are our main, on the client side, we use TensorFlow JS, we use some of the mobile. There's a couple of others that are related to other things, NumPy, Pandas, and sklearn. I couldn't give you a lot of details on those, but I wanted to mention those because those are our major tools.
Okay, so it sounds like you have mostly in-house, or you're doing most of it in-house. You're not using third-party APIs or commercial solutions,
Right,
or repackaging
exactly.
them.
Yeah.
You're doing it yourself.
Yeah.
How about you, Vern?
Yeah, so it's similar for us. I think the time we started it was 2016, 17. So some of these like SageMaker things had not yet come out. So we use some of the same technologies, except like we run our own microservices by ourselves. So we use Kubernetes, and because of that, we prefer Golang quite a lot. So when I think for TensorFlow, most of our TensorFlow is in the cloud. So a lot of the machine learning models are in the cloud, and for retraining them, we use Python and do it there. But for serving the machine learning models, we actually did it in 2017, which is before SageMaker came out, actually 3-4 months. And we'd already deployed it in Vastly. So we use our own Kubernetes, we use Golang with TensorFlow. And a lot of the reasons we built it ourselves was that we wanted to keep the latency, the interaction latency between our TensorFlow model and the client API, especially when I talked about the application optimization. Right at the beginning of the call, you want to know like what is the starting bit rate. You can't take like tens of seconds to do something like that. So we basically try to bring it down to 200 milliseconds. So bring the TensorFlow models as close to, so like CTN it as close to the end users as possible. And so that would be like 50, 100 milliseconds, and then give it 100 milliseconds to like find the answer that you're looking for. So we've not done benchmarks on SageMaker, but like a lot of the SageMaker currently is available only in the US and Europe, which would currently defeat the purpose of using it globally, especially for the application API. So we've not actually explored the models that are available today on a commercial level. But what we found was that the hard part was not actually delivering this. I think the tool chain that's available today, it took us like a few people for like 3-4 months to figure out how to serve this in a performant way with a small team, especially a startup. I think that's commendable. So there's a lot of tooling already available in open source to do that.
How about you, Vijay?
So I think by and large, most of our model development and model research, including coming up with new algorithms, is done on open source tool chains. Specifically, if we end up using some sort of deep learning, then you cannot really escape from Keras and the toolkit there. But more than that, there's more to machine learning than deep learning, of course. And within, for instance, when I do my modeling work and I do my algorithmic work, I typically tend to favor R. But I have folks in my group that work on Python. To a great extent, if you look at it from the R&D perspective, the tool chain itself doesn't matter as much as it does when you're done with modeling and you want to deploy this as a product. At that point is where you have to decide what are the bounds on latency, what are the bounds on expectations, and then either see if there's available C++ models, for instance, or see if you can create microservices, see where you can place them. This is where all the edge computing and all these other constraints come into the picture. But from just doing R&D, I think we use mainly open source. I kind of try to shy away from cloud-based solution. Part of the reason is that the data that we have is private, so we do not necessarily want to upload it to a cloud provider unless we have some sort of strong NDAs, etc. But another part is that we also have our own data centers, and we have GPU machines and stuff where we can run these fairly large jobs.
Yeah, I want to follow up on the last topic. Maybe this is my last question is, how are you going to maintain pace with someone like Google or Microsoft or Amazon that they have far more engineers than you're ever going to get working on this stuff. They have more data to train on, and they have a cheaper data center cost of service because they have this massive scale. So
Absolutely.
I mean, everyone up here actually sounds like you're all using open source and trying to do it yourself. Like, so what's your approach to be different than the cloud providers? Let's start with Vijay.
So I think that's a very good question, and I don't know that there's one answer or one ring that'll fit them all, so to speak. But generally speaking, from my point of view, what Google and Amazon try to do is to try to create general solutions. So if you take a look at Alexa, if you take a look at Echo, they train them to be, they train them across various domains, or they train them without respect to a particular domain. And typically, at least so far in machine learning, the machine learning is a product of the training that it receives. And it could very well be that what they train it from a general perspective doesn't quite carry over into, let's say, a call center perspective, where certain utterances, certain words, certain sequence of words, certain n-grams don't really occur in the general population or the general corpus that these machines are trained on. So where I see us doing a lot of work is, for instance, trying to make these machine learning models focused on a particular domain. So we might take a state-of-the-art ASR engine, for instance, and the state-of-the-art ASR engine is going to make some mistakes because the word error rate is non-zero. It is non-zero. So the question then is, how can we take the output of that state-of-the-art, ASR is automatic speech recognition, transcription. How do we take the output of that ASR engine and further reduce the errors? So I don't think it's wise for us, or being smaller companies, at least for Varun and I, Comcast is pretty big, to go head-to-head against the giants, but I think we can add value by creating these filters that make better what they produce.
Varun,
yeah, so I think my take on this matter is whatever is available today with Google and Amazon are typical broadly computer vision speech analytics, and what we do with the data that we have is mostly about metadata related to a call. So that's a lot of numbers and bit rates and similar things, which means that you can't really use the same. You can use the same kind of technologies, but you can't really take the same method. Can't take the same model straight up. So we have to train our models anyway. As I said, I think the TensorFlow serving part That's improving vastly, and especially Google's pushing a lot of money in Google Cloud to make that happen. So it's just a matter of time when we would basically give up our microservices for theirs, especially as they deploy globally, right? So today, as long as they're only in the US, that doesn't help us quite a lot unless all our customers were here or the end users were all here. But as they move global, I think that is one part where we would just delegate that responsibility to them. But like still building the models are still like not something that we can pick up off the shelf for the type of problems that we're solving. We do speech analytics, we would definitely like go down that path and see we do what Vijay does, like train our own audio systems or just use something from off the shelf.
Any else have a question?
Yeah, I was going to make a similar point. You know, no matter how big or small you are, the tools only get you so far, and they're really only implementing the convolutional networks, neural networks stuff. You know, you still have to have an understanding of your data problem. And you have to collect the data. You have to build the models. You still have to tweak it. So, no matter what, at least up until now, there isn't like a magical solution that covers all machine learning types of things. You still have to be an expert in your area and know how to craft the data and the models to solve the problem you want to solve.
We have a few minutes left. Are there any audience questions before I take all the time?
Thank you. Is there a good machine learning algorithm for time series analysis? Especially, you were saying, Varun, that you're doing some work on the in-call analysis. Could you expand on that more?
Yes, so in our case, we'll use a lot of clustering. So a lot of the time series analysis tends to be breaking down the call into clusters and then figuring out what that impact is. That is one part of it, but we generally tend to use like a lot of clustering algorithms. Gaussian mixture models are similar to get around these problems. K-nearest neighbor, K-means clustering, a lot of these simple systems. We started using ANNs for some of the time series analysis, especially now that we have a corpus of user feedback, which starts to make sense. Like if people start to say like this call was bad because X happened, then we start to like go and look for that behavior within the time series. That's another place where we're looking into.
Your traditional models are ARIMA and ARIMA-X, for instance. More recently, there's been work coming out using recurrent neural networks for time series analysis as well. Recurrent neural networks. RNNs. Recurrent.
Yeah, question for Vijay. That's very good presentation. So, like you have like production system. Like, how do you adjust like those production model for like unknown cases, right? You cannot build like a language model for everything, but you deploy one and then it's working, and maybe you have some customer come in and you have unknown text. And how would you like redeploy? Like, how often would you do that?
So, I mean, I think clearly good software engineering practice dictates that you handle all the cases, and the stuff that you don't know goes in the default case, right? So a very quick answer to your particular question is that if the customer says something and we extract the entities from that sentence, we extract the relationships from that sentence, but those entities and relationships don't match anything that we know about, we simply say that, you know, could you please repeat your question? Or I do not know, you know, what this sentence means, right? As simple as that. So now you could be a little bit more fancy and try to, at that point, you know, run yet another neural network model that would try to parse that and try to extract, you know, take those extracted entities and act upon them in some way. But chances are, you know, you may succeed, you may pass, you may fail, but by and large, you basically, you know, can stop the dialogue by saying that, you know, I do not know how to deal with that.
How would you like incorporate this to your like future models? Would you like do some reinforcement learning? You do some like
Yeah, but see,
or just supervise,
reinforcement learning
label it.
or any type of learning where your target moves is problematic, because that's not true of right. So for instance, if I'm trying to train a model to predict stock prices, I know stock prices are going to go high or they're going to go low. So my model has to be sensitive to the fact that the target is moving. On the other hand, if I'm going to train a model to recognize anomalous SIP messages, I don't want my target to move. I don't want an attacker to come in and start training my machine learning model to recognize anomalous messages as good messages, right? So in that case, I want to nail down my target. So there's no one answer. It depends on the specific application that you are using the AI for. Remember, no computer has passed the Turing test yet.
Yeah, absolutely. Thank you.
We have time for one more question.
Actually, that gets me a question for Vijay. You mentioned earlier about trying to understand the context of the sentence based on if there is noise in the network, in the telecommunication channel, you can still understand the context. How would you transplant that to different languages, for example, or different dialects even, and a place like, let's say, India, where you speak 3 different languages in one sentence? So how would that learning work? And maybe that learning might come in the way of relearning, because one person might have a certain context in which they build a sentence, and some other persons, like somebody from New York or somebody from Texas, might have 2 different contexts of how they build a sentence.
So 2 answers to your question. One is training means a lot to these things. So using a different language or using hybrid languages means you have to provide enough training examples. Okay. Right. The second answer to your question is somehow we seem to assume that these language models are going to be infallible and they're going to be better than humans. In one sense, nothing can be better than humans. When you and I talk, even though we're talking face to face, there's lots of ambiguity. I may say something that you may misrepresent. If you do not ask for clarification, then in your mind, what I said was misrepresented. We can't solve that particular problem with machine learning models, right? So training and I would say to a certain extent resetting your expectations. If 2 humans talking, between themselves have ambiguities, we cannot assume that a human talking to a machine is going to result in a conversation that is completely unambiguous.
Not exactly the same, right? Because humans have emotions and whatnot, but machine is that I'm not emotionally attached with that.
Well, that's where effective computing comes in, right?
Oh, yeah.
We are trying to teach these systems to be emotionally sentient to a certain extent. Many reasons, for many reasons. Medical is one reason, having machines talking. So if you take a look at the studies in hospital rooms, many people press the button and call the nurse, not because they want something, but because they just want somebody to talk to. Or they just want, some form of communication. So you could imagine these voice bots or voice chat type of avatars that are the first point of contact that can hold an emotional conversation with the user before the nurse is fetched. Right? So there's many reasons why you want these emotional agents type of things. If you look at another example, there's tons of papers out there that talk about depression in students at universities and how that goes unrecognized and untreated and often results in fatal incidents. So again, if you had some sort of an emotional, construct that would at least, interact with the student and raise some stuff early on, that would be one reason why we need such things as effective computing. I didn't. So I didn't say that the depressed student is talking to a depressed machine learning algorithm, right?
Well,
so if I'm writing this bot to be more antidepressive, then certainly I would not tell it to be depressed. No, again, you are conflating too many things in one thing, right? Effective computing is trying to mirror the human emotion. If the human emotion is sadness, that's not to say that you want to mirror sadness itself. If the human emotion is happiness, then you want to enhance that happiness.
We'll have to adjourn this session for now, and maybe next year we can have a topic. It's too bad that Douglas Adams is no longer with us, or he could moderate an excellent discussion about depressed robots. But this has been a really interesting panel. Thank you all very much.